In this video, we're going to talk about the first part of Chapter 9, which covers computer networks. We'll just restrict ourselves to the beginning of the chapter, which discusses network topology, and in other videos we'll cover the later subjects in that chapter. Okay, so the first thing to talk about is just to realize that the basic issue of how you connect quote-unquote nodes is not new. Matter of fact, we've been dealing with it pretty much as long as there's been civilization. Okay. We have roads to connect our houses. We have transportation networks to connect our cities and our countries. We have various other sorts of networks that do things like, take trash from homes to, central collection points and on to incinerators or landfills or what have you. So there's, lots of different sorts of networks besides computer networks. Okay. There are, however, basic sets of questions that come up regardless of whether we're talking about moving trash or, FedEx goods or packets in a data network. Okay. And the most basic of those is how we connect one place to another. Okay. One way to connect them is what's called a mesh topology. Okay. And the idea behind a mesh topology is actually fairly simple. In a mesh topology, every node or point is connected to every other node or point directly. Okay. And you have an example of that here on the right of this in the figure labeled A. So let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 nodes represented as these gray boxes. And what I've done is I've created a set of point-to-point connections between every pair of nodes. So this particular node in the upper left, for example, well, actually, now I'm looking, there is no connection between this one and this one. I guess I missed one. But there should be a connection directly between this one and this one. There are connections to these three on the right. There are connections to this one. There's another one here, down here, so on and so forth. So basically, every node is connected directly to every other, or it should be. Okay. For a very small number of nodes, this is a feasible topology and may actually be an optimal one for certain types of movement. Okay. The main advantage of a mesh topology is that because everything is connected directly to everything else, there is relatively high capacity. Okay. So this node can be talking directly to this one, this node can be talking directly to this one, this node can be talking directly to that one. Lots of different quote-unquote conversations or movements of things can occur simultaneously because there are so many different ways to get from one node, because basically every pairwise combination has its own dedicated pathway. Okay. Of course, the flip side of that is, well, look at the complexity. Look at the number of lines involved in this network. There's a lot of connections. Okay, if these were roads, that would be a lot of concrete and asphalt. If these were data connections, using wires, there'd be a lot of wires you would have to lay, be they copper or fiber optic. Okay, regardless of the specifics, the point is, when you have that many connections, you've got relatively high expense. Okay, and you've got relatively high complexity. All right, so clearly this 10-node mesh topology here doesn't work very well if we scale things up. I mean, imagine hundreds of nodes or thousands of nodes, okay? There's a combinatorial explosion associated with this mesh topology. And probably more important than that combinatorial explosion is simply the fact that we don't necessarily need a direct connection between every node and every other node. Okay, so for example, if you think of 30 computers and 30 offices in a typical floor of an office building, we don't really need connections between every single desktop and every other desktop because, frankly, there isn't a lot of traffic that goes from one desktop to another. There's probably a lot of traffic that goes from each desktop to a centralized server. There's probably a lot of traffic that goes from each desktop to, say, the email server or Google or some other internet resource. But there's not a lot of traffic between the nodes themselves. And because there's not a whole lot of traffic between them, it really doesn't make a whole lot of sense to create all those connections that would connect every pairwise set of those computers in those offices. Okay. So that same sort of issue, arises in physical networks as well, and therefore we very seldom see the mesh topology used in any significant large-scale network, be that a computer network or a transportation network. Okay. Instead, what we see is some form of shared connections. Okay. And by sharing those connections, we reduce the complexity and reduce the cost associated with that. Okay. However, in order to ensure that the network is relatively efficient, we have to properly size each of those connections in order to avoid bottlenecks. Okay. So for example, down here in diagram B, what I've done is I've taken the same 10 nodes, the same gray boxes, but instead of creating connections directly between each one, I've created a series of shared connections. So for example, looking up here on the right, upper right of this diagram, I see these 3 gray boxes are connected by, think of this as a LAN if you like. Here's a little LAN that connects just these 3 boxes directly. But that LAN in turn connects to a dark line here running from top to bottom, which is a shared connection that connects the 3 at the top and the 2 at the bottom. It also connects to this other dark line that runs left and right on this diagram that gives me a connection to these 5 nodes out here on the left. Okay. So in essence, I've got a layering of these shared connections. Okay, some of these groups of 2 or 3 nodes share a relatively low capacity connection, denoted by the relatively thin line, and then I have higher capacity connections, noted by thicker lines, that connect each of those smaller connection points. Okay, so in terms of the number of lines, or think the number of roads or the number of wires that are laid out here, clearly I have far fewer. Okay. However, the size of the wires or roads differs. Okay. The roads that just connect a few nodes directly are relatively small. The ones that connect amongst groups of other nodes have to be a little larger because they're going to carry more traffic. Okay. And as we started the discussion, realize that these same sorts of trades-off apply whether we're talking about data packets, moving across a local or wide area network, and it doesn't matter what the data is. Is it downloaded movies? Is it email messages? Is it packets supporting a real-time, distributed game? Who knows? Okay. Are we talking about mail and freight? UPS, FedEx, United States Postal Service? Are we talking about trucks, cars, planes, trains, what have you? Okay, these same sorts of trade-offs. Okay, how do we share connections? How do we minimize cost? How do we properly size those connections in order to avoid bottlenecks? These same issues show up over and over and over again, whether we're talking about data, whether we're talking about transportation, or whether we're talking about movement of goods. Okay, there's a concept that is, some people kind of take it for granted. They know it's there, but they've never put a name to it. But we need to formally define it here because it's so ubiquitous within computer networks. And the concept is what's called a store and forward system, or a store and forward network. Okay. The idea behind a store and forward, well, actually, I like to summarize it using the often overused, amusing little quip about people in Maine, and the idea goes, somebody's driving around Maine and they're kind of lost and they're looking to get, I don't know, they're looking to get, say, from Portland to, I don't know, some other town, and they pull into a gas station and they ask the guy and they say, hey, how do we get to Portland? And the guy says, well, you can't get there from here. You got to go somewhere else first. Okay. Well, that pretty much embodies the concept of store and forward. Okay. And that is everybody, back to the idea of mesh, everybody is not connected directly to everybody else, okay? You got to go to an intermediate spot and then connect to a different road, and that takes you to the next town over. And then you get on the highway, and that takes you to the other end of the state. And then you get off the highway onto a local route. That connects, 5 different towns, and the one you want is all the way at the end of that highway, okay? So this idea of store and forward is simply that, there are steps along the way, and each of those steps represents a spot where whatever it is you're carrying, be that data, be that packages, be that mail, may have to stop temporarily to change from one road to another, or to be offloaded from one truck and onto another, or to be offloaded from a local area network to a wide area network, or say from a wireless network to a wired network. Okay. So the idea is at various points along the way that connect these different pathways or networks, okay, you may need to temporarily store the data, okay, and then once there's an opening, once there's a gap in the traffic into which you can insert that data, now you can forward it on to the next destination. And the way we get from sender to receiver is by a series of these store and forward steps that make a complete path from point A to point B, or from sender to recipient. Okay, this diagram down below tries to sort of capture that idea. Think of the boxes here that are white as end nodes. They're businesses and homes. Okay, so and think in terms FedEx or UPS or somebody like that. So I run an eBay business out of my house, and I've got a bunch of stuff I'm selling, and you bid on it and you buy it. So here's my house here in the upper left hand corner, and here's your house down here on the lower right hand corner. So I need to get a shipment from my house to yours. Okay. Well, where's it going to go? Well, assuming I have UPS pick it up at my door, a UPS truck is going to come by. It's going to pick it up at my door. It's going to also make a bunch of other stops around my end of town, but eventually it's going to wind up at a terminal of some point, a warehouse, if you like, or a transfer station. Okay. At that point, it's probably going to be unloaded off that truck and loaded onto something else. Okay, maybe it's loaded onto a bigger truck, maybe it's loaded onto a train, maybe it's loaded onto a plane. Okay, and now if we're talking about, actually, let's skip from UPS to FedEx because I'm a little more familiar with that. So say this box right here is your local FedEx office, okay, or your local FedEx airport office, if you like. Okay, so at this point it gets loaded onto a plane, and off takes the plane, and maybe directly, maybe indirectly, it winds up somewhere in Tennessee. Okay, somewhere outside of Memphis, Tennessee is the U.S. National Federal Express hub. And all those shipments go into Tennessee, they all get unloaded into Tennessee, and then they all get put on planes to their destination. Okay, so out goes that plane late, in the wee hours of the morning. It flies to this location, which is the airport hub, of the destination site. Okay, and from there, it will presumably be loaded onto a truck for delivery to this particular business down here on the right. Okay, so these gray nodes in the middle, the big one I'm calling the central transfer point in Memphis. These smaller ones would be local air freight offices. Okay, and clearly there'd be a lot more of them than what we're showing here in Federal Express. But the idea is at each of these gray boxes there is a temporary storage of what's being sent, and then an eventual forwarding either to another one of those gray boxes, or eventually, hopefully, to the end destination point. Okay. Once again, this issue of sizing. Okay, clearly the hub in Memphis had better be pretty big, better be able to handle tens of thousands, hundreds of thousands, or millions of packages per night, whereas the hubs in, say, a regional center, say in Albuquerque, don't have to be nearly as large as the one that's in Memphis. Okay. And of course, the individual packages may get aggregated and disaggregated as we go along. When they're picked up at your house and put on a truck, your shipment is aggregated with all the other ones that are currently on that truck. Okay. When it gets to the airport and that truck unloads and 28 other trucks unload, all that stuff gets shoved in one or more containers and they get stuffed onto the plane. That's another level of aggregation. Okay. We get to Memphis, we unpack all those crates, we repack them to go to their ultimate destination. They've been re-aggregated, but once they get to the airport office at the destination site, now we start disaggregating them, and that may involve several steps. So forwarding and aggregating and disaggregating individual shipments or packets of data, if you like. These are common concepts, once again, both in computer networks and in physical or transportation networks. Okay. So this brings us, well, basically what we've done is a very roundabout introduction to the idea of network topology. Okay. Network topology is kind of a wide-ranging topic, okay, and it has both physical and logical connotations. We'll come back to those, okay. But really what it's concerned about is the organization of communication channels and nodes for message transport, okay. And there's two different ways to look at it. The easiest one to think of is the physical one, okay. And the physical one boils down to a very simple question. What is connected to what? Okay, what is connected directly to what? And by extension, what are the indirect connections that connect what to what? So for example, the desktop computer that I am currently recording this video on has a physical Cat6 connection that runs from my computer up into the ceiling, out into the hallway, down the hallway, and connects to a switch in a very small hub or a switch down the way that connects several of my computers. Connects the one in this room, connects two of my computers in ASM 2107, and I think there's at least one other. Oh, my laptop docking station is also connected to that. Okay, so that's a very physical topology. Each of those four computers, quote unquote, have a physical connection to a switch in that room down the hall. That switch in turn has a wire that runs back up through the ceiling and it connects to another switch in our server room. Okay, so the actual arrangement of wires and what's at each end of each wire constitutes the physical topology. Okay. Now, the logical topology, I'm going to briefly define it here, but then we're going to ignore this until later in the chapter. The logical topology is not concerned with so much with physical, it's how do messages go across this network. Now you might say, well, don't the messages have to follow the physical topology? Well, yes, but they don't have to follow the entire physical topology. And depending on what kind of a network it is, they may follow a very direct or very indirect path. So we'll come back to that discussion later. For now, let's concentrate on the physical. So what are the common physical network topologies? Well, we've already talked about one back at the very beginning. We talked about mesh topology. But you will note that that one is absent from this list we have here. And the reason it's absent is for reasons we've already discussed. Mesh topology is feasible for very small networks, but it's simply not feasible for very large networks because the number of connections required is a combinatorial explosion. Therefore, the complexity and cost is also a combinatorial explosion. So we need some sort of shared connection system, and the three most common shared connection systems are showed here in the bottom: star, bus, and ring, and they're actually listed in descending order of frequency. So star is by far the most common, bus is the next most common, ring used to be common, pretty much is not seen anymore, but I put it in here just for completeness. Okay, so let's start with star topology. Okay, in some ways star topology is probably the simplest to grasp. And the idea here is quite simply that all quote-unquote end nodes are directly connected to a central node. Okay, so backing up a bit, think of the white boxes here as end nodes. Think of the gray boxes here as central nodes of various sorts. Okay, so the idea in star topology is all the end nodes, think desktops, laptops, tablet computers, what have you, okay, are directly connected by wires, if you like, to some sort of central hub or switch. Okay, this is by far the most common physical topology. It's the way almost all wired networks are set up today. Okay, the advantages of this are pretty straightforward. It is very simple. For every end node, there is exactly one wire to connect it to whatever the central node is. Okay, it's very maintainable, primarily because of its simplicity. Okay, so for example, in a typical office building like mine, there are one or two wires coming out of every office. They go out through the ceiling or under the floor, out the door, they get routed through the hallways, and eventually they come to some sort of central network wiring closet where this particular, Sorry, I had to pause to grab a pencil here, or a virtual pencil. So each end node has a wire that runs, down the hallway, usually over the ceiling or under the above the drop ceiling, gets to some sort of network closet at which there is some sort of hub. Okay, and that's where those network connections go. Okay, so that central node is typically in some sort of central wiring closet. Okay, so advantages here: simplicity, maintainability. Okay, primary disadvantage. Well, the disadvantage is if the central node fails, if this hub in the middle fails, then basically the whole floor is dead. Okay, so if the central node to which my 5 computers are connected dies, all 5 of my computers are disconnected from whatever is upstream. Okay, now 20, 30 years ago, that was considered a fairly significant disadvantage, frankly, because electronics weren't quite as reliable back then as they were. Okay, network hubs, whatever was sitting in that central wiring closet, those things failed. Okay, they didn't fail all the time, but they would fail with some regularity, and when they failed, bang, everything connected to them is basically cut off. Okay, in the modern world, we expect our electronic devices to run reliably forever, and by and large, they do. It's not that failures never happen, but they're much more physical failures are much rarer than they used to be. Devices are also smarter in terms of recovering from failure. Many network devices automatically detect a failure, automatically reboot, automatically come back up and reconnect all their devices without any human intervention required. Okay. Now, clearly, that doesn't protect you from, what happens if the ceiling in the network closet starts leaking and dripping water on the thing. But the bottom line is failure of central nodes is relatively rare, therefore the disadvantage of star topology is rarely encountered, and the advantage is simplicity, maintainability, and the ensuing or the concomitant reduction in cost associated with that are simply too great to really consider any other option. Okay, next possible topology, bus topology. Okay, the idea behind the bus topology is actually think of this. The easiest way to think of this is to think of the street on which you live and all the other houses on that street. And I'm just talking, from your residential street, from its connection at one end to another road to the connection at the other end. So say you're on, the 1200 block of, pick a, Maple Lane or something like that, and there's 20 houses in that 1200 block. Okay, the street that connects those 20 houses can be thought of as a bus. Okay, all end nodes are directly connected by a driveway to that common communication channel, Maple Lane. Okay, there is no central node to speak of. Okay, so if, say, your house here, you want to, walk to this house down here, you go out your driveway, you walk down the street, you go up his sidewalk, and bingo, you're at his house. Okay, if this house in the upper, or if you want to go from this house in the upper right down to here, you want to carry over a plate of brownies to say hi to your new neighbor, you walk down your sidewalk, you walk down the street, you walk up their sidewalk, knock on their door, and you give them the plate of brownies and say hi. Okay, so in a sense, everybody's connected to everybody else, but it's not a mesh. It's because you all share this common street called Maple Lane, and because you all have a direct connection to it, your sidewalk or your driveway, or both. Okay, so what are the advantages of this? Okay, well, this is a simple wiring layout. It's actually simpler than star. Well, not a lot simpler, but it is simpler. Okay. The other big advantage, especially as compared to star, is there is no central point of failure. Okay, there is no central point of failure. Okay, note there is no hub in here, as there was back here. So when wiring drips on the closet, wiring drips in the closet it's not going to matter as long as that wiring has a good plastic coating that protects it against the protects it against the water. Excuse me. What's the disadvantage? Well, the disadvantage of this, well, here, let's paint you a picture here. Let's say it's 7:30 in the morning on Maple Lane, okay? And everybody on Maple Lane works at the same place and goes to work at the same time. So at 7:30 in the morning, exactly at Maple Lane, 20 people walk out their front door, get in their cars, and try to pull out onto the street. Well, can that residential street handle 20 people all at once entering it? Probably not. Okay. So for a relatively brief amount of time, maybe a half a minute or a minute, there's going to be quite a bit of congestion there on Maple Lane, and some people in their driveways are going to have to wait while the traffic passes before they can actually get on to Maple Lane. Okay. The idea here is that because the channel is shared, in this case the channel is the street, okay, only one quote-unquote conversation can occur, okay, for the amount of time it takes for, that data packet, quote-unquote, to pass from point A to point B. Okay. Same sort of thing happens, say, in a wireless network. If I've got a wireless network and I've only got one frequency for transmitting data across it, if I'm talking on the wire, if I'm transmitting data on the wireless network, you've got to wait. Okay, or there's got to be some sort of round robin scenario where we take turns using the capacity of that channel. So this line running down the middle here, that's the shared channel. It's only got a certain amount of capacity, and if all 5 nodes here want to talk at once, chances are 4 of them are going to have to wait. Okay, probably not enough to wait very long, but they do have to wait. Okay, so big advantage, no central point of failure, simple wiring layout. Disadvantage, because we're dealing with shared connections, there's the possibility that somebody's got to wait. Okay. Whereas in the star network, if all 5 of these nodes want to transmit directly to this central switch at once, no problem doing that because they've each got their own dedicated connection in order to do it. Okay. Last topology, I'll cover it ever so briefly, ring topology. Every end node is connected directly to 2 other end nodes, and the set of connections form a loop. Okay, so this node at the top is connected to this node here on the left and the one over here on the right. The one on the left is connected to the one on the bottom. The one on the bottom is connected to the one on the right. So we've got 1, 2, 3, 4 wires running, each one connecting 2 nodes, and the wires form a loop. Okay, note they may not form a perfect circle, but the pathway that connects all of them forms a loop. Okay, advantages of this. Well, first is you can actually get a fairly long maximum network length here, okay? Because each one of these nodes is relatively short, each one of these connections is relatively short, and each node here is what's called a repeater, and we'll define that. Well, actually, I guess we'll define that in Chapter 8. So whatever message comes in, that if it's not intended for this destination node or this node, it will repeat it onto the outgoing link. Okay, because each time you repeat, you're generating a new signal. These rings can actually get very large, much larger than could be a bus network. Okay. They also have relatively low susceptibility to EMI, assuming we're talking about electrical wired connections here, because once again we have relatively short links. Okay. Disadvantages, well, pretty obvious here. Number one, any one of these nodes fails and the ring is broken. Okay. So any one of these fails and the ring is broken. Okay. Now obviously I've only shown 4 quote-unquote desktop computers here, but if this ring is going to be connected to the internet, well, there needs to be a 5th box in here somewhere, which is some sort of device that will connect to other networks and eventually to the internet. Okay. But the failure of any one of those devices disables the entire ring. Okay. The other issue you run into here is complex wiring and rewiring. Say I want to add a 5th desktop here. Well, where do I put it? Well, if I'm going to put it, say, right here, okay, then I need to break this connection here, connect this node to this one and this one to this one. So in essence, I'm rewiring 3 nodes in order to add 1. Okay, that's complex wiring and rewiring. Oops. Okay, so for those reasons, you just don't see ring anymore. It's just pretty much doesn't exist. Well, will it come back in the future? Who knows, but doesn't look likely. So here's a quick exercise to see how much you understand this. What are the physical topologies of the following common quote-unquote networks? First one, city streets. Second one, cable TV. Third one, wireless computer network within a home. Well, let's take a quick look at some of the possibilities here. Let's see if I can. Here's my web browser. Let's start with city streets, and let's start with orderly city streets.
Here's a map of central Manhattan. Sorry about that. I should mute my cell phone when I'm doing these. Okay, so here's a map of central Manhattan, or Central Park. Okay, and you'll notice Manhattan, like a lot of other cities, especially cities in the Midwest, has a very grid-oriented structure. Okay, so the avenues all run north-south, more or less north-south. Okay, and these streets all run east-west, and they're all numbered consecutively. Okay, and forms a very nice grid. You've got occasional deviations from the grid. Yes, take a look at Broadway here. It kind of runs, a little differently than the avenues and the streets. But by and large, this is a pretty grid-oriented structure. Very typical of large cities, as I said, particularly in the Midwest. Chicago, Columbus, Ohio, Indianapolis, places like that. Okay, not that typical of older cities or cities that weren't designed around a grid structure. So, what kind of topology would you consider this? Well, if we look back at our list of topologies here, star, bus, and ring, well, it really doesn't look like any of those diagrams we already saw. Okay, and in fact, this is not. Okay, this is actually somewhere between the star and the mesh topology. Okay, we don't have a situation where every node is connected to every other, but we do have a situation. So each of these smaller streets, to some extent, you could think of as a bus. Okay, but those smaller streets, note, they cross a whole bunch of avenues. Okay, so streets don't cross other streets, but they cross a whole bunch of avenues. The avenues, in turn, cross a whole lot of streets. Okay, so in some senses, you could think of this as a star, but in other senses, you could think of it as a set of buses interconnected in a mesh framework. So every node is not connected to every other node, but every street is connected to every avenue, and every avenue is connected to every street. And so you wind up with something that's not quite a mesh, but it's heading in that direction. Okay. Let's take a quick look at Albuquerque. Okay, here's a chunk of Albuquerque. Notice that at the large scale level, we kind of look like a grid structure too. Okay, particularly in the Northeast Heights. Okay, because we've got these half-mile roads, Girard, Carlisle, Washington, San Mateo, that run more or less north-south. Okay, and are all exactly a half-mile apart. Ditto for the east-west ones, Lomas, Constitution, Indian School. But as you drill into some of these grids, well, some of these half-mile squares, well, you find that some of them, like this one here, say, okay, I mean, there's your classic grid. Okay, but then you get some neighborhoods. Here's the next one over, north of Lomas, east of Carlisle. This one's God, I don't know. God only knows what that one is. Okay, so the bottom line is, city streets, they don't neatly fall into any of the categories we've talked about. Okay, some cities, grid structure predominantly, and you can think of that as sort of a close cousin of the mesh, although not quite the mesh. Okay, but the streets themselves are shared connections. The streets may be interconnected in a mesh pattern, but the end nodes that are on the streets, each street itself, particularly between intersection points, you can sort of think of as a bus. Okay, now let's talk about cable TV. How's cable TV set up? Well, I have a diagram here of a typical cable TV setup. Let's talk Albuquerque here. There's an office just north of Manal. I think it sits between Rhode Island and Tennessee, although don't quote me on that. And that's the central Comcast office in Albuquerque. Or in cable TV terminology, that's a head end. Okay, how do you know it's a head end? Well, if you look outside of that office, you'll see a whole bunch of satellite dishes. Okay, and that's where the network feeds come in. That's where your ABC and your NBC and your TBS and your MTV and God knows what else, or all those signals are being downloaded across those satellite dishes. Maybe you also have an antenna, although that would be kind of old-fashioned, where you're receiving signals from elsewhere. But primarily it's an issue of satellite dishes. Okay. Also notice there's probably a studio inside that building, and there's a fiber optic connection that connects that studio, so for the local access channels or what have you. So Where to from the head end? Well, you've got fiber connections running out to various parts of the city. Now we're only showing 4 nodes here, but there's probably more like 4,000 or 40,000. Okay, you got fiber connections to each of those nodes, and basically you got one node per quote-unquote neighborhood. And neighborhood, think 2, 3, 4 square block area would be typical. Okay, from those nodes you have a coaxial cable TV wire, if you like, running basically throughout the neighborhood, okay? And each house connects directly to that wire, okay? So what do you got here? Well, you've got actually an interesting combination of bus and star topology. Looking within an individual neighborhood, you have a bus topology, okay? Each of these houses is connected to a cable TV line that connects to a central cable TV line, but the bottom line is the same signals running back and forth to all the houses. Okay, and if you are, say, have a cable modem which you're using for your internet connection, well, you may not realize it, but even though they say that cable modem gives you, I don't know, 20 megabits per second or 50 megabits per second, you're sharing that capacity with all the other houses in the neighborhood because that cable TV connection, that coaxial cable connection, is in fact a bus network. Now, once we get to the nodes are connected in a star fashion to the head end. Okay. Now, this is also a fairly simple diagram. In a very large city, and Albuquerque may actually be large enough for that, you may have a head end connected to, say, 2 nodes for the Northeast Heights. Those nodes in turn connected to 2 other, so say 10 nodes for various neighborhoods within the Heights, and then each of those having a bus network. So there may be multiple levels of this star configuration. But looking at the network as a whole, we have a combination of star and bus. Okay, very common for cable networks. All right, what about wireless computer network within a home? Well, here's another diagram. I'm sorry, it's kind of fuzzy because it was kind of small and I blew it up. But here's a pretty typical way in which a home network would be set up. Okay, so you've got a cable or DSL modem, okay, which is connected somehow out to the internet. If it's a cable modem, we just saw how it was connected out to the internet. It was connected, to the bus network that is your neighborhood cable TV network. Okay. Then there's a connection from that to a wireless router. This is a multifunction device which both serves as an internet router and a hub for the wired network and a hub for the wireless network. And so typically this thing will have some wired connections, and you may have one computer close by that's connected by an Ethernet cable, but other computers in the house, particularly the notebooks or laptops or tablets, are going to connect over the airwaves. Okay. So what is the topology of just the wireless part? The wireless part would involve this wireless access point here in the middle and these 2 computers showed down here at the bottom. Okay. Well, you may not realize it, but that's actually a bus. Okay. It doesn't physically look like this, but the reality is it is a bus. Why? Well, because we're using a fairly narrow part of the radio frequency spectrum, typically a channel that all of these devices are sharing. Okay, and if it's a shared channel and say the notebook wants to send a packet to the wireless access point at the same time this computer wants to do that, well, one of them's going to have to wait. And when a packet comes in from the internet and it's going to be sent out from this wireless router to, say, this notebook, well, it's going to be sent on to the airwaves. The notebook and the desktop computer are both going to quote-unquote hear or see that packet, but only the notebook is going to respond to it because that's the one that's destined for it. Okay, so the wireless portion here is definitely a bus network. On the other hand, looking at this as the central access point, what we have is a bus connected to this, wired connections connected to this, and a DSL connection connected to that. So if I look at this upper part of the diagram, what I'm really seeing is a star. So once again, a home network taken in its entirety, both wireless and wired components and connection upstream somehow to the internet, is a combination of a star and a bus. Okay? And that in fact is a recurring theme you should be thinking about. Most Wired networks are stars, but most wireless networks and some wired networks, such as cable TV networks, are buses. And therefore, viewed in the large, most networks are a combination of physical star and physical bus topology. Which one's used for which? Well, it depends. Wireless networks, by their very nature, are buses, whereas wired networks, usually you'll go with star because of the inherent advantages. Although sometimes, as in cable TV, star is a little too expensive, at least at the neighborhood level. Okay. So anyway, that concludes this part of the video discussing topologies. We'll come back to the later topics in a different video.